Yeah, so thank you very much for the invitation to speak.
Oh, let me introduce you maybe, and then I will leave it with. Okay, so welcome everyone to the IC testing seminar. So today's seminar is joined with the MATFIS series. I'm very happy to have Kevin Costello from Perimeter, who will tell us about the associativity of one-loop correction to the celestial OPE. So Kevin, over to you.
Thank you so much for the invitation to speak. So what I'm going to be talking about is some work I've been doing for the past couple of months with Natalie Paquette. And the goal of our project is to relate the celestial holography program developed by Strominger and friends. We want to relate it to twisted holography on twistor space. So this is the long-term goal. Well, so what I want to talk about today is a kind of maybe more detailed analysis of some features of celestial holography. And at the end of the talk, I'll explain how this connects to the twistor space. So I'm not sure if people have come across celestial holography before. I'm sure people have seen talks about it, but I should remind you anyway. So the rough idea is the idea of celestial holography is to relate a four-dimensional quantum field theory, and you want to relate it to a two-dimensional CFT, which lives on the celestial sphere. And the way this should work is that states, I'll explain in more detail. There's some details to be said here, but states should roughly correspond to conformal primaries. Amplitudes to correlators. And for us, the important point is collinear limits. Which is one has two on-shell amplitudes. When their momenta become parallel, one gets a singularity. That singularity is called a collinear limit. And this is supposed to correspond to the OPE. So what we want to investigate today is the associativity of this. So the associativity of the OPE will be a strong constraint on the collinear limits. And the question we want to ask is, does this hold? Okay. So we need, of course, to ask this question in a particular model. So the model we're interested in is Selfjoule gauge theory. So just to remind people, the fields of Selfjoule gauge theory consist of the usual gauge field, and an adjoint valued anti-Selfjoule 2 form. And the Lagrangian is that expression where I just integrate B against the anti-Selfjoule component of the curvature of A. So the reason this is an interesting thing to consider is that we take Selfjoule gauge theory plus the term G Yang-Mills squared equal trace B squared is equivalent to ordinary Yang-Mills.
I have a question.
Mm-hmm.
So when you integrate out the B, I guess you are going to get FA minus whole square, right? That is the understanding. So FA minus,
right.
but FA minus is not the entire field strength, it's just the anti-self dual part. So how do you get ordinary Yang-Mills?
Well, you get full Yang-Mills, to be perfectly precise, you get full Yang-Mills with a certain theta angle. Because A minus is like half FA minus star FA. So that FA minus wedge FA minus up to some constants, you get FA wedge FA plus F wedge star F. So this term here is a topological term. And this is the usual Yang-Mills term. So the precise statement is that when you integrate at B, non-perturbatively, you get Yang-Mills theory with a very large theta angle proportional to the gauge coupling, or 1 over the gauge coupling. But if you just treat it in perturbation theory, the theta angle doesn't matter. So perturbatively, it's equivalent. Okay. Okay. So I think this indicates the fact why this is an interesting theory. It's a theory that you can deform to get, honest QCD. So what does this tell us? So this tells us that scattering amplitudes in Selfjoule Yang-Mills in the presence of the operator trace B squared are certain QCD amplitudes. So the way you should think about it, you get QCD by having one copy of trace B squared, some weight x, 1, another copy of trace B squared, some weight x, 2, and so on, and then integrating over the positions of them. Because this is how we deform a theory by a local operator. So we're that would give you all amplitudes of QCD. But if you have only one of these trace B squared operators, that gives you certain QCD amplitudes. So we find with one copy of trace B squared, you get QCD amplitudes at tree level with two negative velocities, one loop with one negative velocity, and two loop all plus. So let's introduce, so in the literature on amplitudes, people like to study amplitudes in the presence of an operator. So what we're finding is amplitudes in the presence of an operator are called form factors. So in sum, form factors of Selfjoule mills are equal to some QCD amplitudes. Okay. Any questions?
I have a question. So in order to get back QCD, shouldn't you be summing over all the possible insertions of trace B square? Because unless you do that, I mean, I guess the understanding is that you have it in the path integral, exponent in the path integral. And when you bring it down, you should really be summing over the entire series, right?
That's correct. But if you study the diagrams and like how many negative velicity states you have, you find that if there's only a very small number of negative velicity states, then only diagrams with one copy of trace B squared happen to appear. So the diagrammatics work like this. So so the vertex looks like plus, plus, minus. The propagator takes a plus to a minus. And then I'll draw a trace B squared like that. That takes in two minuses. And you can convince yourself that the diagrams with exactly one copy of trace B squared are those diagrams I listed above. So that's why I don't find all QCD amplitudes, I only find these really kind of fairly simple ones. Okay, so the goal is to express these form factors in terms of a chiral algebra, well, of a 2D CRT. So to explain what's going on, I need to remind people of the spinor helicity formalism. Which tells us that a null state, an on-shell state, is represented by a pair of spinors. So the momentum looks like that. Let's see what's going to next. So what we want to do I'm going to build a chiral CFT, really a chiral algebra, where the plane it lives on has coordinate z, and one of the spinners, these are two component spinners, will be written as 1z. So if you notice in the expression of the momentum in terms of the spinners, there's some homogeneity, which allows me to scale the first component of one of them to be 1. And then conformal primaries at z will correspond to states in the QFT with fixed lambda. So how do we implement that? So here, I will just write down the generators of the algebra. So there's J, A, or S. A is a color index. This is of spin 1 minus 4 over 2 minus S over 2. And J tilde A or S spin minus 1 minus 2 minus S over 2. And these two sets of generators are going to correspond to the states of positive and negative velocity once I arrange them into a generating function. So that J lambda, this is the current tilde. And similarly for J tilde. So I've just built this tower, and it's all a bit tautological because we've defined it so that tautologically we haven't really done anything yet. J lambda tilde Z corresponds to a positive velocity state with momentum E equals lambda tilde, and J tilde lambda tilde Z corresponds to negative velocity. So this is all really trivial. We're going to get some content. Let me explain the content we're going to find. So we'll give these an OPE. Which matches collinear singularities. So I should say what I'm doing is following what was done by Guevara, Hinwich, Pate, and Strominger, although they only consider the positive helicity sector, but it's pretty much the same. And then something Natalie and I observed is that by thinking about correlation functions, we'll give the Park-Taylor formula for amplitudes. Okay. Okay, so far we've just declared that these are the generators of my chiral algebra, and they're just encoding the states. And I haven't described the OPE yet. Are there any questions?
Yeah, so when you say that J of lambda tilde Z is a positive helicity state with P lambda lambda tilde, what exactly do you mean? Because it's a series, right? In terms of the lambda lambda tildes, and the helicities are defined in terms of the lambda lambda tilde, right? So for
Right,
different terms in the series, the helicities would be different.
So let's say, so what's going on is, if you work on real space, like a state is, f of x is equal to ei p dot x, and p is lambda lambda tilde, and then I expand that in a series and find this expression. So this is like literally the series expansion of that state. So J or S is equal to an explicit polynomial on real space. So therefore, this infinite sum up here is just the expansion of the exponential.
Yeah, and I guess the coefficients JRS would delineate what sort of helicity particle you have, right?
Yes, I mean, maybe a better way to think about it is, if instead of using the usual basis for states, which are eigenfunctions of energy, you use soft modes, then like on real space, these are solutions of the Laplace equation, which are just polynomials. And so these polynomial solutions of the Laplace equation just are the J-orders. And that's perhaps the better way to think about it. So then the OPEs can be thought of what happens when two soft states become collinear. Okay, so you happy with that?
No, I was just concerned how the different helicity particles or states differ when you have different helicities. So the corresponding expressions, how would they differ? So they would differ in the coefficients, I'm guessing, right? Because the lambda lambda tildes would be the same.
Right. So these are positive. So what we've done, like in our chiral algebra, I've just corresponding to the A field and positivelicity, I have one set of generators, and corresponding to the B field and negativelicity, I have another set of generators in my chiral algebra. You can read off the helicity from the spin, you see. So there's a change of sign in the spin. It's +1, that's -1, and that corresponds to positive and negative helicity. Like there's a general formula for what spins you will get for states of arbitrary helicity.
And what determines the spin?
Well, the way I would think about it is, if you think about Penrose showed how the solutions of massless field equations can be written in terms of cohomology groups of certain line bundles in twistor space. And what line bundle is determined by what helicity you have. And the line bundle also determines the spin, because on this chiral algebra, we really have a field twisted by that line bundle on twistor space, because it's really, I haven't really mentioned twistor space yet, but that's the way I want to think of it, how these are built. Okay, so it's okay, I'll go and let's think about how to do the OPEs. So classic amplitudes literature gives formulae for singularities in states when I take two states of momentum P1, P2 are such that their inner product goes to 0. So this can happen if P1 and P2 are built from lambda 1, lambda 2, lambda tilde 1, lambda tilde 2. So if lambda 1 tends to lambda 2, then P1 dot P2 equals to 0. So in our notation, if Z1 goes to Z2, then this goes to 0, and we have a pole in the amplitude. So this is kind of why you might hope that these poles are related to OBEs, because they can happen when Z1 tends to Z2. So let me write the formula for these singularities and then just translate it into OBE language. I need to introduce a little notation. 1, 2 is these angle brackets and square brackets are just the contractions of these spinors. And the poles are, if I have some kind of amplitude like this, and I have two positive velocity particles, and these become collinear, the singular term is dominated by something like this, where this is plus, plus, goes into a minus and a plus. So I replace two states by one state. So this is state is I and j, 1 over I, j. So that I have two positive velocity states. When they come close together, they become one positive velocity state, and I get this polar term, 1 over I, j. Similarly, when plus and minus come together, we get a minus with 1 over ij. And in Selfjoule gauge theory, this is all there is. In full gauge theory, you also find terms with poles in the square brackets, but we don't want those because we want to have a chiral algebra. So as an example, the Park-Taylor amplitude So just so you can see where these poles appear in explicit expressions, I take an amplitude with n states, two of which are negative velocity. This is ij to the 4th over 1, 2, 2, 3, and 1. And you can see exactly these poles appearing. Like when two positive velocity states come together, I get a pole, and I can replace them with one state. This is kind of plus primitive. There's some, I'm suppressing the color factors here. So there's some permutations. Okay. So how to do this in the Carroll algebra? Well, ij is simply zi minus zj. So if we have these poles, we know how to define the OPE.
I have a question.
Yeah, of course.
Yeah, so when you have ij, this angle brackets is essentially means epsilon alpha beta lambda I alpha lambda j beta, right?
Yeah.
Yeah. So when you convert the lambdas to z's, how do you get z? Okay, so you get for one you get 1 and z1, and then the other for the other you get z2 and 1. Is that how you get it?
Exactly. Yeah.
Okay, good.
Right. So here I'm going to write. I just take this formula in this old literature for collinear singularities, and you just translate it into the language of OPEs, and it becomes this expression. And similarly, okay. Great. So this is all pretty straightforward, and we've just translated it into a piece. And what we find, this is an associative Carroll algebra. And you can see that it's Cass-Moody-like. And so following result Natalie and I checked, this Carroll algebra has the following nice features: that conformal blocks of this algebra. Let me quickly say what I mean by conformal block, because the word is used for several different things sometimes. So for me, a conformal block is a way of defining correlation functions compatible with ODEs. So conformal blocks are equal to local operators of Selfjoule animals and correlators in a conformal block are equal to, because this is a tree-level algebra, we haven't built any loop corrections in, it's going to be equal to tree-level form factors. So for example, there is a conformal block for the operator trace b squared and its correlation functions. I put in two negative velocity states. And the rest positive. And I take the correlation functions in this chiral algebra. You just determine this by saying, you know, there's some method to figure out what the 2-point correlation function is, and the rest are determined by the OPE singularities. And this is equal to the Park-Taylor formula. Okay, so great. At tree level, we have a nice chiral algebra. We can relate it to local operators of the Fourier theory we're interested in. And we can use this chiral algebra to compute tree-level amplitudes. It's all very straightforward. We haven't really done anything very deep yet. So we can ask, does this continue to loop level? Yeah.
So when you are saying that you're taking the inner product with trace of b square, are you assuming that the b has a dependence on the lambdas or something in any way? But
no, so well, let's see. So to make sense of this, we have to unravel the statement that conformal blocks are the same as local operators. So I need to figure out a conformal block, the same quantum numbers as trace b squared. So because the Park-Taylor amplitude doesn't have any square brackets in it, we don't expect any dependence on the lambda tildes, and we don't find that. So the way it works is that trace b squared, I look at the lowest part of j tilde, C1, C2. If you just think about the quantum numbers of trace b squared, you find that this has to correspond to C1 minus C2 squared. And then the rest of them are, I can, it's fun to do actually. So if we look at this one, I'll introduce some color. This 3-point amplitude has a pole when Z3 hits Z2 and a pole when Z3 hits Z1. And those poles have an FABC in them. So we're going to find something like FABC Z1 minus C2 squared 1 over Z1 minus C3 minus 1 over C2 minus C3. And that is equal to FABC squared C1 minus C2 cubed C1 minus C2 C1 minus C3, which is the Park-Taylor amplitude. And then we just continue. I don't know if that answers your question, but that's kind of how it works.
No, I was just asking, what role does trace B square play here?
Right, so it defines the conformal block because, so a priori, this is a very funny chiral algebra. There's lots of things of negative spin. So there's loads of ways of defining correlation functions. So in my terminology, a conformal block is a consistent way of defining correlation functions. And these are in bijection with local operators. So you can ask, what is the conformal block corresponding to trace B squared? And it's determined by what it does to two insertions. So we trace, so this, the only role trace B squared plays really is in this expression here. Like if I know I want the conformal block for trace B squared, by thinking about its quantum numbers, and you know this formula must be true.
In order for that, trace B square would have to depend on Z in some way, right? I mean, otherwise.
It doesn't, because these are, see, so it doesn't depend on Z because Z is transformed under the Lorentz group. Z lives in a two-sphere, which is rotated by one of the SU2s in the Lorentz group. Trace B squared is the Lorentz invariant operator. We derive this expression, Z1 minus C2 squared, by requiring that this is a Lorentz invariant, taking into account the fact that J tilde is of spin 1.
Like the gauge field in ordinary, when you do the twistor formulation of gauge theories, the gauge field depends on the lambdas in some way, lambda, lambda, or lambda. Instead of lambda, lambda tilde, you just have lambda, lambda, or something like that. I was just wondering whether B has a similar dependence on the lambdas and through them to the Zs.
Well, I wasn't thinking about the twistor uplift here, but I wouldn't say that B depends on the Zs. I mean, the dependence on the Z is, you know, the states I'm inserting depend on Z, but I wouldn't say B does.
Because otherwise, how would you kind of get the conformal blocks if the B doesn't have a dependence on the Zs?
I suggest maybe we can leave this for the discussion at the end.
Okay, yeah, I think that makes sense. I wasn't explaining very well. Okay, so let's move on to the quantum level. So in the 90s, work of people like Byrne, Dixon, and Kosower, they find one loop corrections to splitting amplitudes. That is to collinear singularities. So they're studying QCD. And of course, when they do full QCD, the expressions they find are quite complicated. And they depend on the cutoff and everything like that. But in the expressions they find, you can look at the diagrams and you can see which ones exist in Selfjoule gauge theory. what they find is that there's, coming from this diagram, so if I have, so I have 2 plus states, these are becoming collinear, then there's a singularity which is determined by a triangle bubbling off like that. And the contribution, these states I and j, so they find this new contribution like that. And there's some particular factors, like number of colors divided by 96 pi squared. So let's ask, does this exist in the chiral algebra? So because it's something where 2 pluses become a minus, it's going to be j 1 jb lambda 2 tilde c2 equals fabc 1 2 c1 minus c2 squared. So now we're going to find there's a second order pole in our OPE, j tilde c. Here we're going to have half c1 plus c2. So I've written it out in a way in terms of generating functions, but if we expand these generating functions and write it in a more explicit way, we find the following expression. Like that, plus half 1 over z times the derivative a tilde c. So this second formulation is just obtained from the first one by taking the coefficients of lambda 1 tilde and lambda 2 tilde. Okay. So question. Does this define a chiral algebra? And the answer is no. It fails to be associative. That is, if you look at the following, so there's a associativity in chiral algebras is formulated in terms of change of contour. It's my z. So if I take the following kind of double contour integral, associativity would tell us that it should be equal to, but it's not, the same expressions integrated in a different way, or one of them on the inner contour of w, plus in the other one, w goes around z. And you just calculate both sides and they're just not the same. So this is not good. So it seems like QCD cannot, it seems, be controlled by a 2D CFT. Or even, depending on how you formulate it, even Selfjoule case theory. If you have a strong formulation of what it means to attach a 2D CFT to it, then that just doesn't work at leaf level. But this can be fixed by a Green-Schwarz mechanism. So if we add to Selfjoule and Mills an axion, with a fourth order kinetic term, there's some very particular constant there involving pi and the number of colors and so on. And we assume a certain Lie algebra identity that trace in the adjoint of x to the fourth is proportional to trace in the fundamental x squared squared. So this holds for my gauge group being SU2, SU3, SO8, and exceptional. In these cases, associativity is restored. So what we can show
hi, could you explain the statement in the language of just the usual correlations of the field theory, like what does this mean? Like what does this special choice of gauge group mean?
Let's see. So I mean, I won't have time to get into this, but so the first way we come across this is by thinking about the twistor uplift of Selfjoule and Mills. It uplifts to holomorphic BF theory in twistor space by the Penrose-Ward correspondence. But holomorphic BF theory has a one-loop anomaly, which can be cancelled by a Green-Schwarz mechanism for these groups. So from that picture, this cancellation is, the anomaly comes from a diagram like this, and it's cancelled by this kind of thing, by an exchange of these axion fields. Just from a purely space-time perspective, I don't know what else to say except that the OPE doesn't, the collinear singularities does not define a Carrot algebra unless this holds.
I have a related question. So when you have the TTOP in an ordinary conformal field theories, you also have a similar term, right? Del T divided by Z1 minus Z2.
Yes.
So in that case, would you still define it to be non-associative?
No, there's associative. I mean, the Virasoro algebra is always associative. So it's not.
But this term is precisely similar to that. You have a derivative on the J and you have a.
Yeah, but I feel like it's superficially similar. I mean, the presence of the derivative on the J, that has to appear for symmetry reasons, because, you know, there should be Z1 and Z2, and it should be symmetric on the permutation of Z1 minus Z2, of Z1 and Z2. So therefore, really, the right-hand side should be evaluated at the midpoint between them, and that explains the appearance of the derivative. So the failure of associativity is not. There are OPEs with second-order poles, and which are associative. The failure of associativity, I don't know. You just check the algebra and it doesn't work. I don't know any other good reason.
Hello. So I had a question. So when does this thing become better in supersymmetric Young-Mills theories? Like,
yes, absolutely. Good question. For supersymmetric Young-Mills theory, annoyingly, this correction vanishes, because in this diagram here, you see, you have trace. You have a kind of gauge loop and a fermion loop, and they cancel.
So there the algebra is associative. This particular
that algebra is associative, yes, but it's associative, but also not that interesting. I think. At least I think the non-supersymmetric ones are more interesting.
So even the minimal amount of supersymmetry cancels this. Is that the statement, or you need?
That's correct. Yeah.
Okay. Okay. One more question. When you say exceptional algebras, you just mean E6, E7, E8? Do you just mean the simply laced ones, or do you also mean?
It also works for G2 and F4.
Also G2 and F4. Okay.
Yeah.
Okay. Thanks.
Let's see. So yeah, there's some literature on you know, this identity appears in literature in anomalies and 6G theories. It's pretty well studied. Yeah. So in the cases when the anomaly is cancelled, so we can show that there exists a quantum Carrot algebra and again it's conformal blocks are local operators of the 4D theory, and form factors are equal to correlation functions in the Carrot algebra. So we were able to match explicitly the one loop all plus QCD amplitude. With the particular correlation function. Using this method. So
I had one more question. Can I consider the gauge group to be a product of these groups? Would that work also?
Yeah, but you probably would you. Ooh. Yeah, I think that should work. Yeah.
Okay, thanks.
Let's see. And actually, there's also some other cases where it works. Just for example, no axion, SU2, and number of flavors is 8. SU3, number of flavors is 9. And there's some other cases you can figure out. But beyond the supersymmetric cases where this this kind of anomaly doesn't happen.
So these are fundamental Dirac fermions. Or
Yes.
what do you mean by NF? So you add Dirac fermions in fundamental. Is that?
Yes, eight fundamental, 8 anti-fundamental.
Okay.
I mean, for SU2, it's symmetry is kind of U16 because fundamental and anti-fundamental are the same. But for SU3, it's really SU9 symmetry. Okay, so I think I will. Yeah, I think I'll stop there unless there's any other questions.
Like, is it clear that the theory is unitary with this fourth order?
No, it's not, but it's not unitary to start with, right? So Selfjoule Yang-Mills is like a non-unitary CFT.
Okay. Okay, yeah. So I guess we can thanks a lot for the talk. And if there are more questions.
Yes, I have a question. So I'm actually interested in the twistor space interpretation, in the sense that here you've studied a holomorphic BF theory from the twistor space perspective, and it's reduced to the BF. And you also have, I believe, an additional term in the twistor space description, which reduces to the trace B squared term. So I believe that's sort of is it a non-local term?
That's right. So the trace B squared term is a non-local expression. So it kind of messes everything up.
Okay, so that leads me to the main question, which is so 4D WZW model, which also can be obtained by reduction from 6D Chern-Simons theory instead of holomorphic BF. So in that case, 4D WZW is equivalent to anti-Selfjoule Yang-Mills equation. So is there a way whereby we could do something similar using this 4D WZW? Yeah, but you would, I mean, the equivalence to the anti-Selfjoule Yang-Mills equation is only a tree level equivalence. So if you look at the scattering amplitudes of 4D WZW, at tree level, they're the same as those of Yang-Mills theory with all plus, which are not very interesting, but they're zero, flat space. But if you were to study the loop level amplitudes of 4D WZW, there's something different. I see. Okay. Because you have to, you have different fields running around the loop. Ah, right. See. Thank you. It's interesting. But...
And so, could you comment maybe on the relation with celestial holography? If like, do you expect that there could be this issue there?
Let's see. I mean, the whole idea that one might hope that collinear singularities are related to OPEs comes from celestial holography. So I should be very clear though. So there's a nice paper of Strominger and who else? Sorry, let's just say Strominger and collaborators, since I'm bad memory. Yeah, Strominger, Ball, Narayan and Salzer. So they also study Selfjoule gauge theory and Selfjoule gravity, but they only consider positive Felicity states. So in there, this issue does not arise, and they find everything works. So it seems to me that including negative Felicity states in Selfjoule gauge theory, you run into a problem. celestial safety.
So I had a question. So let's say if I am interested in trying to compute the one loop beta function of the Yang-Mills, how do I think about that from the chiral algebra? Is there a way to think about it from the chiral algebra perspective? Is it some particular object in the chiral algebra?
No, there's no easy way to think about it because the one loop beta function, from the point of view of Selfjoule Yang-Mills, the one loop beta function comes when I have two copies of trace b squared. When I have two copies of them, they have an OPE, which looks like 1 over x to the 4th trace b squared. When I integrate this, I get a logarithmic divergence even with the one loop beta function. So as we understand things right now, the chiral algebra works best with a single local operator. And then I take form factors for that. But to get the one loop beta function, I need to have two local operators at two different points. We don't really understand that as well.
Okay, thanks. But is that a general statement? It's basically something that works for the loop for just tree level kind of questions, or?
But it's not quite tree level, right? Because there's some, suppose I was to look at the form factors, for example. Suppose for some random reason, I'm interested in the QCD form factors, or like trace of b to the 20. This is a really complicated expression, but a leading term one of the terms in this will be given by the Selfjoule and Yang-Mills form factor. But that term might be at a very high loop number. So even for trace b squared, if I knew enough about Selfjoule and Yang-Mills form factors, I would compute a two loop amplitude.
But yeah, but isn't that confusing? Because you're saying, but then if I would have thought there should be some way of reading of one loop beta function if you're from higher loop form factors and so on. Maybe it's not very direct, but maybe if you could write down some scaling equation, some evolution equation, shouldn't that tell you about the beta functions also?
Well, let's see. So let's write QCD in this way. So what we're computing, and if I take the form factor of trace b to the n, you can have n loop terms with no Yang-Mills dependence. Right, so that's slightly counterintuitive. The issue is that when I pass from the first order to the second order formulation, I multiply b by 1 over g Yang-Mills. Or by some power of g Yang-Mills. I could draw a diagram if that would help. Here, if this is something which takes in a bunch of negativistic particles, and if I have my minus plus propagator and my plus plus minus vertex, I could clearly, do a bunch of contractions, right? So, like this. And that will build a lot of loops, but it's still just in the Selfjoule case.
But so is there a subtle distinction between loops counting in the self-dual Young-Mills and ordinary Young-Mills, in the sense that so this is a higher loop diagram that you've drawn. But if I have to calculate the same object from the usual like textbook Young-Mills perturbation theory, would that be a higher loop computation or a tree level?
Yes, it would be a higher loop computation. And what's going on is when you pass between the first order and the second order formulations, there's a field redefinition where B has to be multiplied by a power of G Young-Mills. So if you take a diagram in the Selfjoule theory, which has no powers of G Young-Mills, you must multiply it by power of G Young-Mills, which has to do with the number of external lines of negativelicity. And that's how those powers come up when you go to the second order formulation. Does that make sense?
Yes.
It's something pretty trivial, but I'm not getting it totally right.
But the power of G Young-Mills could come just from tree level diagrams also, right? I mean, you could just have, I mean, I'm just wondering whether, yeah, how do I see that it's also a loop on the other side? Yeah, maybe, yeah. Like, do you know what is the like ordinary Young-Mills diagram which computes the same thing as what you have drawn? Is that
no? It's the same diagram, I think.
where you replace B with what? This cross B with this B insertion with what?
Just want to that the negativelicity component of the curvature.
Oh, okay. Okay, thanks.
Yeah, sorry, I wasn't very clear, but it.
So, what exactly do you want to have this associativity property?
Why do you want to have it?
Yeah. Because
well,
the
if
term
there's
is
a
still
CFT,
consistent, right?
Yeah, I mean, if there's a CFT, then it's associative. Otherwise, it's not a CFT. I mean, what you know. It's associativity just says that if I have correlation functions in the CFT and I take some bunch of operators together in different orders, it doesn't matter which order I've taken those limits.
So can I ask a question on that point? Actually, so is it a problem then for self-dual Yang-Mills that you don't have this associativity? And the reason I ask, I don't want to put words in anybody's mouths, but I was not too long ago watching a talk where afterwards Strominger was making some comments. He was making comments in the context of gravity, which you're not discussing, but he was almost going to the extent of saying that a four-dimensional theory that doesn't have the property that it's realizable as a CCFT should be considered as part of the swampland. So coming back to my question, is there anything wrong with it from the four-dimensional point of view? Or just it is what it is, you know?
I mean, I think my perspective is a little bit different. So I think like having this feature is really special and points to some kind of integrability, so that these theories are analogous to integrable theories in 2 dimensions. For integrable theories in 2 dimensions, there also is, you can do algebra to compute scattering amplitudes because they satisfy beautiful algebraic properties like the Yang-Baxter equation. So from my perspective, this is kind of analogous. So I wouldn't have expected QCD to satisfy this. QCD is way too hard. It's no integrable features. It's completely unsolvable.
Okay, thanks.
I find it surprising that there's any that satisfy this at all. So, but
And so is it possible that, let's say, some four-dimensional gravity theory, maybe with some matter, could satisfy this?
yeah, so there's work by in progress by Roland Biddleston, Atul Sharma, and David Skinner, which are they're analyzing analogous questions for gravity, and it's quite a bit harder, but they do find broadly similar story. And as I said, as Strominger and collaborators, if you take your Selfjoule gravity to mean you only look at positive velocity, then everything works perfectly.
Hi, I have a question. So we went to this particular identity about the gauge with the gauge groups and so on because you proposed this fix using this axion and so on. But how unique is this fix, this particular form of axion and this modification and so on? Like, couldn't there be something else which will work for more general groups or something?
Yeah, no, I mean, you're right. You can do, let's see. I mean, I came upon this fix by thinking about twistor space, and maybe there's other ways to do it. For groups of low rank, you can fix it using matter. There's other fixes that I know about. You can take SUN, then you take axion and matter, where I think NF equals NC. That's all. I think that's also a fix. But basically, as far as I understand things, these are the only ones that I know about, where you play around with the axions and the matter, and you have to satisfy some trace identities. Okay, I think I should get going now.
Okay, let's all thank Kevin for the fascinating talk.
Well, thank you very much.
Yep. Thank you. Let me end the meeting now then. Bye.